Hi everyone, my name is Yuan. Thanks for coming to my talk today. Today I'm presenting our work about visual exploration of machine learning model behavior with hierarchical surrogate rule sets. In recent years, machine learning models have been widely used to assist humans to make a decision. To understand the model's behavior, one of the popular methods is to train a surrogate model that approximates a original model's prediction behaviors. And surrogate rules are usually assumed as interpretable and easy to understand. However, in real life, it is still challenging to analyze a set of surrogate rules. The first challenge comes from multiple features. Given a set of rules like this, it is hard to figure out how multiple features interact with each other and contribute to the final model decision. Let's try to simplify this problem a little bit. Given the two surrogate rules here, why does the value of bills paid on time lead to different model predictions? A direct way of analyzing is to extract the shared condition, bills paid on time equals to median or high. See how the model decision distribute when a condition is applied, and then see after adding more conditions how the distribution of model decisions change. If you're familiar with decision tree, here a rule is equivalent to a decision path. In this case, we can see that applying hierarchical structure can help us see the change of model behaviors more clearly. However, another challenge comes from the long rules. It is still hard to read through the whole rule set like this. Here are two rule sets approximating the same model. Of course, the second rule set on the right contains shorter rules and fewer rules are easier to interpret. But let's take a step back. Because these rules aim to approximate another model's behavior, how faithful the rules are is also important. But how do we measure it? Here we introduce rule fidelity to measure the faithfulness of a single surrogate rule, which is the purity of the actual rule of the actual model output distributed in the data subgroup described by a rule. Specifically, it is the number of data samples of the major model prediction divided by the total number of model predictions. Let's use the rule path on the left as an example. Its rule fidelity equals to 77 divided by 77 plus 23, which is 77% in the end. After calculating the rule fidelity of rules with different number of conditions, unfortunately, we can see a really common case. Shorter rules are easier to read, but usually cover more instances with lower rule fidelity. So the second challenge here is not just about longer or shorter rules. It's actually a trade-off between faithfulness and complexity. In real life, different people with different goals tend to have different preferences. Such preferences also change along the rule exploration. As such, we want to quantify the trade-offs of faithfulness and complexity and enable users to customize their preferences when generating surrogate rules. Therefore, in this paper, we have three goals. We aim to generate rules that fulfill user-defined preferences on faithfulness and complexity with hierarchical structure. For these rules, we also want to design a proper visual design to better support surrogate rule exploration for model understanding. In the rest of this presentation, I will first introduce the algorithm of generating a set of hierarchical surrogate rules, and then we'll introduce SURE, a visual analytics system integrating interactive rule generation and analysis. In the end, we'll discuss some lessons learned from a user study and an observational study. To deal with the trade-offs between complexity and faithfulness, we introduce a few rule properties. For each rule, we care about rule fidelity, which is what we just introduced, rule coverage, the number of instances that can match the rule, rule length, the number of conditions in the rule, and feature granularity. We use number of bins to control the granularity level of the feature values. For example, if number of bins equals to 3, the feature values can be generally interpreted as low, medium, or high. We also care about the rule set level properties. including rule set size and data coverage. To quantify users' preferences, we allow people to apply constraints on the rule level properties. For example, the minimum fidelity each rule should reach, or how many data samples a rule should at least cover. Also, the maximum number of conditions the user prefer, as well as the number of bins they want to apply to each feature. As for the rule set properties, we use them as optimization objects. That is, we want to use as few as possible rules to cover as many as possible data samples. After defining the rule constraints and optimization objectives, we follow a four-step rule set generation algorithm to generate hierarchical surrogate rules, which includes, firstly, surrogate random forest initialization, and then rule extraction from pruned trees based on rule constraints, and then rule set optimization, in the end, the reconstruction of rule set for the final hierarchical rule set. Please read our paper for more details about this algorithm and the experiments we have run for evaluation. Since the trade-offs usually change over time, we need to provide more support to interactively generate and explore rules. As such, we designed Sure, a visual analytics system for surrogate rule exploration, where the users can interactively set parameters to generate rules for exploration. Also, they can filter, compare, and reason about rules by using visual analytics techniques. Here, I want to highlight the visualizations we provided to support people for rule analysis. We first include a basic rule representation in the system, which is a list of text rules. To better support the hierarchical analysis, we then include a hierarchical text list. To support the analysis of different features, we further propose feature-aligned trees, where the conditions with the same features are aligned in the same column. Because the text representations can be directly read and interpret, we want to know whether new users can easily use feature-aligned trees. So we conducted a user study with 24 volunteer students from NYU. We found that participants can interpret and search visual information from feature-aligned trees with very high accuracy. In addition, most participants agreed that it was easy to interpret the rules from feature-aligned trees and easy to search information from feature-aligned trees. To better understand how users analyze rules in practice and how Sure can provide support, we conducted an observational study with 7 domain experts from Capital One. Each study took from 90 minutes to 2 hours, and we asked the participants to think aloud when they used Sure to analyze rules. Based on this study, we contribute a task categorization for rule interpretation after qualitative analysis, which include 3 analytical focuses and 7 categories of rule analysis tasks, as well as how Sure can support these tasks. For example, one of the mostly performed tasks is rule search and exploration. A user may want to answer a question like, what are the nodes that have higher fidelity, which is fully supported in Sure. There are also some interesting behavior patterns. For example, we found users switch between different rule visualizations when conducting different analytical tasks. We also found that users tend to analyze shorter rules. They wanted to build their own rules. Also, users with different domain knowledge background tend to explore rules in different ways. Please read our paper for more details. In conclusion, in this paper, we contributed HSR, an algorithm that generates rule sets based on the user-defined parameters of faithfulness and complexity. We designed Sure, a visual analytics system that supports interactive rule generation and included multiple visualizations of rules. We also conducted an observational study based on Sure, which leads to a task categorization of rule analysis. Thanks for listening. I'm open to any questions.